Let's do the one-way between ANOVA analysis. When do we use the one-way between ANOVA? We have one independent variable, it's categorical, 3 or more conditions or levels, and it's a between design with one continuous dependent variable. What is the goal? To test if there is a difference among the 3 or more means. The data entry is identical to the independent samples t-test. You have a participant column, a participant variable, that's ID type. You have an independent variable column, that's nominal, which is categorical and tells you who belongs to which condition. Remember, participants only belong to one condition. There's condition A, B, and C in this example. And the dependent variable is continuous. I'm going to be silent, but this will show you the buttons you press to get all the results and analyses you need. And one final time. So the first thing we're going to look at is the pattern. In order to do that, I like to look at Jamovi's graphs. We can see here that condition A is less than condition B, which is also less than condition C. That is a pattern that we are seeing. Now, what does this mean? That depends on your example. These examples do not have context, so you will have to figure out what this means for your problem. In terms of my p-value, which is next, I look at this part of the output, and I specifically look at the p-value. Is that less than 0.05? This is significant. Now, that means there's some difference among the 3 means, but it doesn't pinpoint where those differences are. Now, the effect size for an ANOVA is called eta squared, and it has an identical interpretation to r squared. Eta squared times 100 equals percent. So in this case, my eta squared is 0.88 times 100 is 88%. What does that mean? If this were a true experiment, it means my IV causes 88% of the DV. In a correlation study where you have a categorical IV like identity that's not randomly assigned, you would say my IV is associated with 88% of the DV. Now, this also has small, medium, and large values. An eta squared of 0.01 or 1% is small, 0.05 or 5% is medium, 0.16 or 16% is large. Unfortunately, Jamovi does not provide a confidence interval for this statistic. So all you can say is that in your data, the effect appears to be large. With this test, with the ANOVA, we call it an omnibus test. It just tells us if there's some difference among the three means. It doesn't pinpoint it. To pinpoint the difference, we have to run post hoc tests. Each of these tests that compares each of these two means has its own pattern, p-value, and population effect size. So in this example, we're comparing condition A to condition B. That has its own pattern, p-value, and population effect size. The population effect size for these postdocs is, again, Cohen's d, and it will give you the 95% CI of Cohen's d. Then we got to compare A to C and B to C. So we have three comparisons, each with their own pattern, p-value, and effect size. So the first postdoc I want to do is I want to look at my pattern. Is condition A different than condition B? I have to look at this post hoc table, so find that in your output, and you find the line that compares condition A versus condition B. It is this first line. Now that's the pattern. We see the pattern. Condition A is less than condition B. We find our P2 key, that is less than 0.05, that is significant. We get our Cohen's d, that is negative 3.21 in our data, in our sample, that is large. 95 CI is from negative 5 to negative 1.23. Both of these are negative large. Our second question is condition A less than condition C? I mean, the pattern suggests it's less. So is it significantly less? So I wish Jamovi put condition A here. It does not. You just have to carry down this label. So condition A versus condition C. That's our next comparison. Is it significant? Yes, it is. Less than 0.05. And this is a large effect in the data, and it is an estimated large to large effect in the population. Now we want to compare condition B to condition C. We see the pattern. B is less than C. Is that significant? Yes, it is. This is a large effect in our data or sample, and it's negative large in our data or sample. It is also a negative large effect in the population to a negative large effect in the population. Remember, Cohen's d is 0.2, 0.5, 0.8, small, medium, large.